Hello everyone, my name is Wei Chen. I come from University of Bordeaux. The topic of my presentation is an improving approach for DOM-based web test suite repair. I will present it from 5 parts. First, background and motivation. It will include the problems that developers are facing. Second, our approach, web test suite repair. Third, empirical evaluation. We will do empirical evaluation to validate our approach. Fourth, we will present the empirical results, include the conclusions. Fifth, the future works that we will do in the next steps. First, for the background and motivation, Figure 1 is web application Joomla from release 3.6 to release 3.7. For the sake of clarity, we will refer to these two releases as R1 and R2. This is an example of Joomla, which includes 3 web pages: the login page, the page of control panel, and the search page. Joomla is a real web application. It is a content management system which allows its users to build websites. And the pages for screenshots. With 3 web pages. During the evolution of web application Joomla from R1 to R2, certain HTML elements have changed. For example, in the third page, the featured articles are moved to featured articles here because the submenu fields and field group are added in release 2. Figure 2 is the test case in 2 releases of Joomla. A test case composed a sequence of user actions that simulate actions performed by a user on its browser, such as open a web page, click button, or input something. As we can see from the top of Figure 2, developers write a test case for release 1 of Joomla. The test case consists of 7 actions from line 1 to line 7. Each action corresponds to the user operation from tag 1 to tag 7. Input username, input password, click login button, and click menu articles. Click submenu featured articles. Then input the search contents, and then click search button. When this test case is executed, it will automatically launch and run Google Chrome to simulate user actions on the website. To input username, password, or click login button, which are almost automatically. However, with the web evolution, the test case is broken due to the changed selector. Let us give two examples of breakage. First, non-selection breakage. A locator can target the DOM element in R1, but the locator is unable to select the target elements in R2. For example, the layout of button login do not change during the web evolution, but the locator is changed from login to login button. So the test case is broken because it targets a CS selector that does not exist in release 2. This example is a kind of non-selection breakage. Second, for mis-selection breakage, the locator of featured article in R1 is child 3, but in this, the layout was changed. So now the featured articles is child 5. So when we execute this test case, the selector cannot target the real featured articles. It targets fields. So it was misselected. For this example, it is the mis-selection breakage. Figure 3 summarizes the problem of web evolution. Developers write test suites for web release 1. And during the web evolution, developers submit web release 2. But the test suites can work well on release 1, but they cannot work well on release 2. So these broken test cases are need to evolve to correspond to web release 2. Then it can work well for the web release 2. Our goal is to generate the evolved test suites by repairing the broken actions. So to solve the problems, we propose web test suite repair. Figure 4 is the architecture of web test suite repair. We try to execute the initial test cases on release 1 to generate test suite graphs for release 1. And we also run test cases on release 2 to generate test suite graph for release 2. And then we compare these two test suite models to repair the test cases. Okay. The test suite model is 5-tuple structure S, U, A, L, C. S is a test suite that consists of a set of test cases representing all tests. U is a set of URLs representing all web pages of test cases. A is a set of actions representing object events in the URLs, and actions in different URLs are different. L is a set of links that may follow edges between different actions. AI to AJ means AJ executed immediately after AI. C is a set of candidate actions after each test action. For example, TS1 and TS2 are in the set of test cases S. The URL of each action is stored in MongoDB. All the actions of test cases are in the action set A, and the link A1 to A2 means that A2 are executed is performed directly after action 1. During the execution of the test case, we cross the candidate actions after each action. For test suite graph, it is only a simple example. In this figure, the test suite graph is more complicated in an actual web application that contains more test cases and more actions. After generating the different model, we then compare them to repair the broken test cases. It first compares the test cases to find the broken actions and broken test cases. It then compares the candidate action to generate the candidate set. Then we try to identify a substitute action from the candidate set as a replacement of broken action to repair the broken test cases. Then we do empirical evaluation. There are 3 research questions. First, is it possible to generate test suite graphs for 2 different releases of a web application? Second, is it possible to automatically and efficiently repair these test cases for web applications by comparing their test suite graphs? Third, how effective is our test suite evolution method? Table 1 is end-to-end test subjects of web applications. We choose 3 real web applications from GitHub. There are many releases for each web application, and we choose 2 main releases for each web application. Table 2 shows that the test suite graph that we generated for each web application. The test suites, the URLs, the actions, and the links. We also record the time it takes to generate the test suite models. Let's take Joomla as an example. the release 1 and the release 2, we do both to generate the test suite graph. For release 1, the test case do not broken because all the test cases are useful for release 1. But for release 2, we run the test suite on release 2, but there are 38 were broken. For the URL, we record the URL, but during to the broken action, the URL are not enough. And during the update process, we can generate all the URLs. And for the actions, for R1, we can generate 204 actions. And for R2, because of the breakage, we cannot get all the actions. And during the update process, we can generate all the action. And for the links, okay, for the time it takes to generate the test suite model, we find that the cost of time spent to build test suite graphs is related to the number of actions, and they have a positive linear correlation. Table 3 is web application test suite repair results. We compare our approach with Water. Water is an existing tool that was proposed by other authors in 2011. We use the same web application and the same test cases to run on our approach and on Water. We compare the repair ratio and we compare the execute time. From table 3, we can see that our repair ratio is a little better than Water, and the execute time is almost the same. So we can conclude that our approach is effective to repair test cases for web applications. Another finding is that as the number of broken actions in each test case increase, the repair ratio will decrease. For example, if there is only one broken action in a test case, the repair ratio is high. It's easier to repair for only one broken action in the test case. But if there are 4 broken actions in a test case, or more than 4, it is harder to repair, and the repair ratio is lower. For the future works, first, we experiment our approach to the web applications with bugs to study how do bugs affect the usefulness of this test repair approach. This is because we do not include the bug influence during our test repair. And second, we collect user feedbacks on our technique to make our approach better for web test repair. Third, we update our algorithm to continuously improve the efficiency of test suites repair and try to deal with value cost breakages. Okay, thanks.